This is a magic square. In a magic square, adding the numbers in the cells through any direction, vertical, horizontal, or diagonal, sum to the same value. 4 plus 9 plus 2 is 15, 3 plus 5 plus 7 is 15, etc. No such set of numbers has ever been found for only square numbers in the cells. A naive brute force search for solutions is very difficult. There are 9 free variables here. Even searching from 1 through 1,000 gives us 10 to the 27 possibilities. I'm going to guide you on this long journey of this problem and what I ended up figuring out. I'm going to label each cell here from A to I. Starting from this setup, some relations can already be written. For example, the 8 expressions on the far left almost equal each other. They just represent the summing of each row, column, and diagonal. The second and third columns simply use the equalities from the left column. I highlighted one of them in particular as I'm going to be using that for the next slide. This is because of the high restrictions of having 4 pairs of variables equal to each other. Those 4 equations are what you get when you try to sum all the rows, columns, and diagonals that pass through the center cell. I'm now going to tactfully take 2 of the equations from the previous slide and try and get them equal to each other. First, I'm going to rearrange the second equation to what's on the third line there. The goal now is to get that equation to look like the equation on the first line. The simplest thing to do is to make a squared equal to 2c squared and I squared equal to 2d squared. However, there's more than one way to do this, and in the next example, I set a squared equal to g squared plus 3c squared and I squared to f squared plus 3d squared. The last equation is a full generalization of all the possible substitutions you can put in for a squared and I squared to get the first equation. At first, it might seem like a step backwards because we're introducing yet another variable. However, n does have a definite solution. Here I'm just using an equality that was found earlier, a squared plus I squared equals d squared plus f squared, and performing substitution on that. And now that n is defined, that could be substituted back into a squared and I squared to get an equation without n at all. There is a way to greatly reduce the a squared and I squared equations, and it's going to involve yet another previously found equation, c squared plus g squared equals d squared plus f squared. Here I'm basically just adding 0, which is to say I'm adding a minus c squared d squared plus c squared d squared in order to cancel the denominator value. After a lot of algebraic work, there's our a squared value, and now I'm going to do the same process with I squared. Notice how A and I are defined only in terms of G, C, F, and D. And now because we found these values for A squared and I squared, we can actually do similar substitutions for all the other letters. Now it's time to go back to the original table and make all those substitutions so that everything is defined only in G, D, C, and F. Now this is pretty good, but we can get rid of one more variable and make the table look a little simpler. I'm going to reintroduce the new definition of h squared and try and get rid of the variables c and g. And there we go. With only a couple assumptions about what a and I should be, we now have a table with a reduced set of 3 variables. If you were to try to take this new table and add all the cells in each row, column, and diagonal, you'll still get the same value for each of them, and they will be a specific value of 3d squared plus 3f squared over 2. This is a good way to check our work because all the sums should be the same value. Now, out of the 9 cells of the new table, 3 intrigued me because they were so similar in structure. These 3 values were so special to me, I gave them their own names: n1 squared, n2 squared, and n3 squared, as they should still be square values. Now, after a lot of messing around and doing some algebraic gymnastics, I found something interesting about this form. Now, when trying to brute force integer-only solutions for this equation while treating d plus f over 2 as its own unit, I found out that there's a right triangle hidden in this. The solutions that make up d plus f over 2 are just the long leg of a right triangle, and n1 is the hypotenuse of the right triangle. What this means is that if you are given a right triangle, you can use the long leg and the hypotenuse to figure out what df and n1 should equal. You end up with a system of 2 equations to solve here. For this example, df equals 119. That basically tells us that we need to split 119 into 2 factors. And 2 of those factors should also allow the first equation, d plus f equals 24, to be equal. In this example, 7 times 17 equals 119, and summing the factors gives you 24. Since all 3 equations on the left follow the same structure, you can do the exact same process for the other 2. This led to the next idea. What if I were to try and redefine everything in terms of only the n1, n2, and n3 variables? In order to do that, we need to isolate each of the variables d, f, h in order to get their n1, n2, and n3 counterpart. Fortunately, this is surprisingly easy. Now going back to the dfh table, I now know 6 out of the 9 substitutions to make to get them only in terms of the n variables. And since I already know what d, f, and h are in terms of only the n variables, it's relatively easy to convert all the other cells. Checking my work, if you were to try and do column, row, and diagonal sums, they should all give you 3 n1 squared, which is much nicer than the previous table. Notice that in the dfh table, we have 3 guaranteed squares in specific cells, but in the n1, n2, and n3 table, we also have 3 guaranteed squares in 3 different locations. In my notes, I like to reduce and simplify the writing required for these tables, and so I just remembered which space they were in, whether dfh or n1, n2, n3, and just defined each cell in terms of 3 separate number values. So for example, in the top left cell, That triple just represents f squared plus h squared over 2, while in the n1 and n2 and n3 table, the top left cell simply represents n2 squared. At this point, it seemed pretty clear to me what the next goal should be, trying to find 3 guaranteed square values in the remaining cells of the table that didn't have them. For this, I wanted to start with the n values, since they don't have fractions in them, and set each of the 3 remaining cells to k1 squared, k2 squared, and k3 squared. Now to do a similar exercise, which is to get n1, n2, and n3 defined on their own and only in terms of k1, k2, and k3. Now that the 3 variables are defined in terms of k1, k2, and k3, I can take the table of n's and convert them all into k's. Checking my work again, performing all the sums possible, all of them equal to minus 3k1 squared plus 3k2 squared plus 3k3 squared. And here's the simplified form. So for example, the top left cell, minus 2, 2, 1, is actually minus 2k1 squared plus 2k2 squared plus k3 squared. Now at first it just seems like it was wasted effort. After all, we still have 9 variables to deal with. However, the set of relations we have is now much stronger than in the first iteration. I've listed some of the equalities on the right-hand side. In fact, you can encode all those equations into a giant matrix and perform one of the most obnoxious row reduction problems I've ever had to do, and end up with a simpler set of equations like the following. With this set of equations, all you need are d, f, n1, and k3. All other variables can be found once you know those 4. And really, you just need 2 out of the 3 for d, f, and n1. If you look at the table on the left, it kind of makes sense. Knowing just 2 out of the 3 in the middle row, you can get the third value. From there, you now know f squared and k3 squared, meaning you can find n3 squared. You now know n1 squared and k3 squared, so you can find n2 squared. And then that makes the first row solvable, and then the second column solvable, and finally the third row solvable. Now this equation right here shows up a lot in the system of equations found earlier. Because of that, I put the most amount of effort in trying to find a solution for this equation. What you're about to see is attempted solution 1. Here I basically just plugged in the equation to Wolfram and tried to get information out of that, and this is what came up. Now that's a pretty nasty set of solutions. Fortunately, all the stuff in the middle there can be shortened down into something much simpler. So I'm just going to call all of that S1 and S2, and I just remember that both of them depend on another variable, n. With this knowledge, I go back and find a few of the equations that looked like that form above and converted them to these solutions. Now that we have these forms, we can simplify the table even further. An important thing to notice is that in the equation a squared equals minus b squared plus 2c squared, a and b can be swapped freely. I use this idea for the bottom 2 equations to get something I can work with. Now, because I have 2 pairs of S1 and S2 equations, they each can have their own n value, which I'm just labeling as x1 through x4 here because I have 4 of these equations. But I'm going to make one more assumption, that for these 2 particular pairs of equations, x2 is going to equal x3. Doing this allows us to get another set of constraints, this time between f, h, k1, k2, and n2. Also notice how the S1 and S2 requirements have just completely vanished. We no longer need to worry about them. Now with these two additional constraints, the table can become even simpler. Now everything is only in terms of h and k1. Time to substitute these back into the table. This is what the table looks like, only in terms of h and k1. And if we try to perform all the sums, they all equal 3/2 times k1 squared plus h squared. But there's one more simplification that we can make. I'm going to pull out one of the cell values and just examine it on its own. And since we are looking for square numbers, I'm going to set this equal to a square number, x squared. Now notice here we get a case of a squared plus b squared equals 2c squared. The second term there, the hk1, we know must also be a square because it exists on its own in the table, and we are looking for only square numbers. From here we bring out those nasty solutions that involve s1 and s2 and perform some simplifications. And here we have a way to express k1 in terms of s1 squared times h. Now if we go back to the table here, that's a lot more useful than it looks. Now that all of k1 is gone, notice how every term in each of the cells has the same factor of h squared. This means h squared can also be removed from all cells in the table, leaving us with just values in terms of s1. And here we see the top middle cell, the middle right cell, and the middle bottom cell are all squares. It's a bit harder to prove. I did this on my own. I'm not including it in the video, but the top left and bottom left cells are also guaranteed squares. So this means we now have 5 out of 9 cells guaranteed to be square, and with just a single variable defined. Now remember that S1 had a specific definition. It cannot be replaced by any value. It must follow the form shown below. Now unfortunately, even with just a single variable remaining, it was still not possible to find all 9 cells being square at the same time. In fact, it's now simple enough to prove that there is no situation where all 9 cells will ever be square. Here I dragged out the 4 remaining cells that aren't guaranteed to be squared. Here I'm going to make an assumption that the second value in that list is a square and assign it to a variable of y squared. Now I'm going to take the 4th value in that list on the left and shape its terms until we can fit a y square in there. Now this value should still also be a square, and I'm going to give it a name, w square. Notice how this again has the form of a squared plus b squared equals 2c squared. It's going to be a bit confusing now, but now there are 2 s1 values where you can plug in a different variable in each of them. I'm going to square everything and substitute y square for the first equation on the top middle. Now what we have here is very interesting. On the right hand side, there's an s1 value in terms of one variable, and on the other side, it's defined only in terms of s1 with a different value. It doesn't really matter what each of the s1 values are at this point, or what z1 or z2 should be. All S1 values must be integers, and in particular, the value on the left must be a positive integer, because the value on the right-hand side is a positive integer. And the only way for that to happen is if S1Z1 is equal to 1. Any other value is going to give a fraction. Now I was using S1Z1 and S1Z2 because I know I was going to deal with two forms of S1 here. But Z1 in this case is exactly the same as the variable Z on the left-hand side of the equations. And if you were to substitute each of those S1 values on the left with 1, you will end up with cells whose values are the same, and that's not what we're looking for here. We want unique solutions to the magic square of squares. Therefore, there are no unique solutions with these given constraints. Now the set of solutions that were found don't actually cover all possible solutions. There is a better set of solutions we can get from this equation. I'm going to show a bunch of examples here where I'm just using integers to find solutions to this equation. Now there's a really interesting pattern here. I'm going to give a first hint as to what that pattern is. All I did was change the middle term. It still equals the same value, it just has a different form. If this doesn't look obvious yet, maybe it will when I change the left value into a different form. The values hidden inside A, B, and C here are all just Pythagorean triples. In this case, A is just the sum of the two legs of a Pythagorean triple, B is the difference of the two legs, and C squared is the hypotenuse squared. And remember that A and B are interchangeable, so A could actually be the difference of the two legs, and B could be the sum of the two legs. This gives us, as far as I'm aware, the true full set of solutions for this equation. Now, after doing a bit of algebra, I was actually able to find 8 of these equations that have the same structure. I'm now going to write solutions for each of these equations, and A and B are simply the legs of a Pythagorean triple. So A and B cannot be any integer, they have to be part of a Pythagorean triple in order for this to work. And since there were two terms that are interchangeable, I'm using plus minus and minus plus to show that that is possible. With this new information, I'm now going to find some further insights that we can make. So here we just found two interesting sets of relations. A8 times B8 must be the same value as A3 times B3, which must be the same value as minus A6 times B6. Similarly, A4B4 must equal A5B5, which must equal minus A7B7. Now let's see what happens if we try and find A and B values that satisfy all the constraints of just one of these equations. This is the lowest product that can be found that satisfies the equation above. Here we have 1680 equaling 3 different factor pairs, 40 times 42, 24 times 70, and 15 times 112. All that's left to do is to use these numbers and assign them to A8, B8, A3, B3, and A6 and B6 and see what happens. As you can see here, this was enough information to fill out the entire table. And all these cells have square values. What's even more impressive is that 7 out of the 8 sums are all equal. Now remember that we had 2 sets of equalities. You can do the same process for the second equality and get a similar table where 7 out of the 8 sums are equal and they're all square values. Unfortunately, there was no way for me to find a set of numbers that satisfied both of those sets of equalities. And I'm pretty sure if there was such set of numbers that were found and satisfy all the constraints that we've discovered so far, we would get a square of squares solution. We can try another tactic where we assume that we know some of the variables and try and define everything else in terms of variables we already know. Now we can multiply this whole equation by a7 and end up with a quadratic which we can then solve. This is because the second term becomes a7b7, which we can then equate to minus a5b5 thanks to the equations on the left. You can do the same process where you multiply by b7 for all the terms, but actually what you end up with is basically the same equation. This means that that equation on the right, with the plus or minus, can be split up into the 2 solutions for a7b7. It's a fairly straightforward process to get all the other a and b values in terms of variables we already know. Notice the 2 sets of a and b values with square roots in them. Remember that a and b must be integers. This makes it a lot more difficult to figure out what a3b3, a5b5 should be. In fact, I ended up with another dead end here. I was unable to find a set of values for a and b that would give us just integers for everything. It was at this point that I basically ran out of ideas, and so I had to go to the internet for help. This integer-only constraint that we have for our equations makes these Diophantine equations. From there, I found a very insightful post on Stack Overflow by this user. I will attempt to explain the concept as simple as possible. Suppose you have an equation of some ellipse, in this case a circle, and let's say that you manage to find a point on that ellipse which has rational values. You then should be able to draw a line through that point, and if the slope of that line is also a rational value, the other point that the line intersects with on the circle is also going to be a set of rational values. Using some clever algebra, this allows us to restrict our solution space into that of the rationals, and from there we can convert it to that of the integers. I'll go through an example shortly. Here's our a squared plus b squared equals 2c squared equation. I'm going to divide everything by c squared, so we can end up with an equation in terms of just 2 variables. And it's okay if we redefine a over c and b over c because they're still rational values. Now for this trick to work, there needs to be a rational set of solutions to this equation. Fortunately, this is easy. The answer is x equals 1 and y equals 1. The following equation is the slope of the line that goes through that 1, 1 point. And something to keep in mind that the slope m must be a rational value. Now to get everything in terms of y and perform substitution into the first equation. We end up with a quadratic equation for x and then we solve for it. There's 2 possible solutions here for x, but as you'll see shortly, one of the solutions just ends up with the value that we already know. Once we know x in terms of m, we can now find y in terms of m. Now here we have a form that looks like a squared plus b squared equals 2c squared. However, we're not done yet because remember, m is a rational number and we have to make this in terms of integers. Here I will set m to some rational number, p over q, and simplify everything. And this is our actual solution for a, b, and c. This is much more advantageous than the previous solution because p and q do not need to be Pythagorean triple values. They can be any integer we want. However, this doesn't make our previous work absolutely useless. In fact, you can switch between these two forms, between using a and b and using p and q. I will set the terms of these two different solutions equal to each other. As you can see, given p and q, we can get to the solution space of a and b. Going the other way is possible. We can go from a solution that involves a and b to a solution that involves p and q. Note the plus and minus operator. We know it can only be plus because if it were minus, then the value on the right would be a negative, but the value on the left requires it to be positive. And there you go. Both solutions found are equally valid. We can now use this knowledge to convert all of our solutions with a and b into that of p and q. Now, after a lot of messing around with these new forms, I've determined that these sets of equations below are really important. They share variables with the two sets of equalities at the top, and they help heavily constrain the space of what the p's and q's are allowed to be. I'm now going to demonstrate what happens if we make an assumption on what these values should be. Here I'm assuming that q7, p7, and q5 can be written in terms of p5, effectively removing one variable. That large expression multiplied by p5 to the fourth, I'm going to substitute it for the value of c. Performing an exhaustive search, I've concluded that c can only have very specific values. These values can easily be defined algebraically. Now what we end up with here is a form that looks like the Diophantine equation we already solved. However, the constant terms in front of the variables are different, and so this is a new equation. Fortunately, we have all the tools we need in order to solve equations of this form. We're looking for a rational point solution, and in this case, it's 1/2, 1/2. Just like before, one of these solutions gives us a value we already knew. After some term rearranging, we now have a proper solution to the above. S is equal to 2 to the power of z. So that third equation on the bottom left tells us a lot about what p, q, and z can be. The first scenario is p can equal 0. However, if p equals 0 is plugged into the first equation, we get no solution. This is because on the left side of the equation can only be positive, but the right side of the equation can only be negative. And if everything were 0, we would end up with trivial solutions, which we are not interested in. The second case is if q equals 0. However, if you took a look at the second equation, we end up with a similar conclusion to the first one. The final possibility is p equals q. I will now show a list of values that p and z can equal, and here we can see that z and p can be expressed algebraically. Here I'm basically making it a parametric solution, with t as the parameter. I'm now going to bring in the second equation on the bottom left. Since there's nothing interesting when r equals 0, here I'm requiring the right-hand side to be positive greater than 0. From here we figured out that t must be greater than or equal to 0. If we were to set t equal to 0 here, we get a trivial solution where r equals plus or minus 1, so we expect t to be greater than 0. Now for the new r squared plus 1 equation, the right-hand side is always even, therefore r squared plus 1 must also be even. We can enforce that by having r equal to 2n minus 1. Note that because of the two equations we have, where z equals 2t plus 2 and p equals 2 to the power of t, t must be an integer. So 2n squared minus 2n plus 1 must be an even integer. However, the first two terms will give you an even number, and the 1 is an odd number. Thus, this will always be an odd number on the left side, and therefore there are no solutions that are non-trivial. So this didn't help us get closer to finding a magic square of squares, but now we know we can't just get rid of one of the variables by having every other one be a factor of it. Now it was at this point that I didn't want to figure out another type of Diophantine equation, and that I wanted to solve a general form of it. As it turns out, it is possible to solve a general form of ax squared plus by squared equals cz squared. And what's strange is I couldn't find any other online resource that had this specific solution that I'm about to give. Because of that, I think it's of great importance, and I will probably make it its own video as well. Given a Diophantine equation of this form, find the general set of solutions. Divide the equation by c squared, and rename a squared over c squared and b squared over c squared into x squared and y squared. This method requires us to find some rational solution for x and y that satisfies this equation. Now create a slope equation that passes through the point x0, y0. The slope value m is constrained to be a rational value that we will call p over q. This should allow us to find an arbitrary number of other rational points that the line crosses for the equation above. This is a quadratic equation in terms of x, and therefore can be solved. Compute and simplify the value of the discriminant. Group terms in terms of m. Note the terms inside parentheses where bm squared and a are. Using the equation in yellow at the top, these can be rewritten into a different form. With this heavily simplified discriminant, now compute x. Note the plus and minus operator. If we only look at the minus, we get a value we already know. Therefore, x has only one solution that we care about. We now have x and y in terms of m and other values we already know. Remember that m is some rational value, p over q. And there's our solution for ax squared plus by squared equals cz squared. X, y, and z must be the following. Going back to the main topic, finding a solution for p5q5 times q5 squared minus p5 squared equals minus p7q7 times q7 squared minus p7 squared was very difficult. It is basically a quartic equation, and in the world of Diophantine equations, that's not something you want to be solving. Fortunately, I found yet another resource, which is a giant repository of these sorts of equations and how to solve them. There are actually 3 different solution sets for the equation that I'm interested in solving, and I'm going to be using each of them and showing that it is likely not possible for any solution to exist. It's at this point where I can't really guarantee that there are no solutions at all, and since I'm also not sure if there are any other solution sets that could be found, the last part of this video is basically going to be a best effort. With that quartic equation out of the way, there now just remain these 2 constraints. Here I use these 2 equations to generate 2 other equations. One is the sum of the 2 equations, and one is the difference of the 2 equations. I'm going to square one of the equations, and then use the bottommost one to perform a substitution into the one above it. This is a quadratic equation in disguise, where here we're solving for p3 squared. Now, since p3 must be an integer, the value under the radical must also be an integer. Through exhaustive search, the only possible v value that could be in there is plus or negative 1. Plugging v back into the topmost set of solutions, we end up with 2 not useful trivial solutions. I won't be talking much in these next 2 examples because they'll use a very similar strategy to the first example. In order for the expression under the radical to be an integer, we only have 2 options. U must equal 0 or v must equal 0. The solution set we end up with here factors down to another trivial solution. For v equals 0, it's the same story. For this last example, we get a slightly more interesting set of solutions. Here u could equal minus v, or u could equal 3v. And this is where I must end it. I've tried all sorts of methods to get some solutions out, but it just doesn't seem possible with the current information. The best that can be done seems to be having 9 squares, but with only 7 out of the 8 sums being correct. But this isn't a full proof, and there are still some leftover possibilities, some which could allow the search to run deeper. But I've worked way too many months on this, and so this is where I must stop. I leave this information out for anyone else willing to take a shot at it.